I'm going to do is, I promised you an example in which numerical approximation leads to rounding errors, which are potentially confusing. And then it actually took me like a little while to think of a good example. So it's good that I didn't just sit here and think of it in class last time. So first, here's the general structure of sort of dynamic range issues that come up with floating point numbers. By default, floating point numbers on a computer, they're typically double precision numbers, so they're represented using 64 bits in the computer. Some of the bits are used for the mantissa, and some are used for the exponent. So the number's kind of somehow packed into 64 bits by default. Of course, you can work with floating point numbers with a much larger number of bits. It's just not as fast, and you have to be explicit about that. Here's an example. I take the number, this notation in Python, 10e100, means it's scientific notation. It means 10 times 10 to the power of 100. So I guess I could have written 1e101. It would have been the same thing. That was kind of a weird way to write it. Actually, that's what I should write, so it's consistent with what I do next. It's scientific notation, not 10 to the power of 100. So if you take 10 to the power of 100 and then add 1 to that, then you get something. And it's being represented using only 64 bits of precision. And then you subtract 10 to the power of 100, and you end up with 0. However, mathematically, you should kind of end up with 1, right? Because actually, as a number, 10 to the power of 100 plus 1 minus 10 to the 100 is 1. So here the calculation is done exactly instead of using floating point numbers. When you use scientific notation, it automatically switches to floating point numbers. But down here, by just explicitly writing 10 to the power of 100, it does all the calculations exactly, and you get the number 1, instead of the number 0.00, which is completely wrong. Any number, it's like 0, none of the decimal places are correct. Okay? You could also do the calculation with, so you can explicitly make floating point numbers with a large number of digits. So if I do real field 1000, that gives me the real numbers, but modeled using 1000 bits of precision. And then you can do the same calculation there. I don't know if this is going to work or not, but we'll see. And notice it does work. If I use less bits of precision, it won't work, but if I use enough, then it does work. See? So there's some like threshold where suddenly you start getting the right answer. Or really the wrong answer. Well, yeah, you start getting the right answer eventually. So rounding errors do not make the answer completely wrong if I use 400 bits, binary digits of precision, whereas if I use less, well, some number less, not exactly 399, but some number less, then you do get rounding errors. So I wanted to construct an example like this, but using a symbolic expression that might come up when doing calculus type stuff. And here's what I made up. So I'm letting A be the symbolic expression e to the power of 100 plus a tiny little number, 10 to the minus 20. So that being plus 1 minus e to the power of 100. You can't just do what I have up above, because it just simplifies it instantly. And so that doesn't work. You're not able to, I can't just construct that expression and then sort of evaluate everything using floating point numbers with this capital N command that I told you about on Wednesday, because it already gets simplified away. However, if you do e to the 100 plus a tiny little thing, plus 1 minus e to the 100, basically these two e to the powers are almost exactly the same, but they're not going to get simplified to 0 because they're not exactly the same. And the simplification rules don't just make them equal to each other. Okay, so this is e to the power of some fraction, which is extremely close to 100. It's basically e to the power of 100 plus a tiny little bit. And then I subtract from that e to the 100 and then add 1. So that's the expression. So it should be very close to 1 because e to the 100 plus a tiny, tiny little thing is like e to the 100 times e to the tiny thing, and e to the 0 is 1, so it should be close to 1. So let's just see what happens. If I numerically evaluate it, I get 0. And remember, the way this end command works, it just takes the leaves in the expression tree and replaces them all by floating point numbers, and then evaluates everything up, and it gets something. In this case, it ends up with 0.000. For the same reason that we ended up with 0 above. Namely, you have a huge number plus a tiny number. You can't even represent that in floating point numbers. So adding the tiny number just gets completely ignored, and then you subtract the huge number to end up with 0. I mean, there's just no way, there's not enough room in a floating point number to represent huge number plus tiny number. It's like, you just can't represent, 10 to the 100 plus 1. However, if you take this thing called real interval field, well, actually, before I do that, I'll do one more. If you just do real field with, say, 200 bits of precision, oops, I haven't reevaluated this yet. If you do real field with 200 bits of precision, notice that you do get a number which is very much not 0. So notice that this was wrong for every single decimal place. It's exactly the same A. It's just that instead of evaluating all the leaves in the tree using 53 bits of precision, it uses 200 bits. If I do this instead with 53 bits for the mantissa, then you get 0, but if you increase it a bit, then you get the correct answer. Okay? Another way you could do this, though, is you can use interval field, and what that will do is it'll guarantee that every digit it's printing out is actually correct, except possibly the last one. And it does that by, so notice, here's what you get. What this does is that every single step along the way, it keeps track of little intervals, so it knows exactly how much precision is left over. And it knows for a fact that every digit in this resulting expression is right, except possibly that too. So here, when you do all the evaluation using 100 bits, you're not really sure about some of these digits at the end. You just don't know. When you use interval arithmetic, you do. Okay?
Shouldn't it be about 1?
Well, this e to the, there is this extra little thing. It's kind of like close to 1, but it's not really that close to 1, because it's 10 to the minus 20. So it's actually right, but let's see, e to the power of 10 to the minus 20. So we're working with very big numbers here. So, well, let's see, real interval field. So the thing is, you're multiplying e to the 100 by that number right there. So it's really close to 1. Is something wrong?
Why are we getting 2 times 10 to the 20?
It's because so when I was exaggerating a little bit. E to the power of 100 times a number that's very close to 1 is very close to e to the 100. But it's not really that close to e to the 100. I mean, it's, so look, we have two numbers here. Alpha is this number. I'll just compute them correctly to 200 bits of precision. And then beta, let's say it's this other, the same number, but without the 10 to the 20 added on. So they're close in the sense that when you print them out, they're going to look pretty similar. Notice they look pretty similar, but they're not really that close because look at what their difference is. It's 2 times 10 to the 23. So in that sense, they're very close. Like if you have two numbers and they look really similar, but there's a big exponent, they're close, but they start getting very different down here. Okay, does that answer your question?
Yeah.
All right, so that's the first thing. Any more questions about this? I won't say anything more about interval arithmetic, but if you ever hear about it or you ever run into precision issues in practice, Google it and learn more. And then use Sage to use it because I think it's more smoothly integrated into Sage than in other places. And it's really fast. Okay, I'll say one more thing. How fast is it? So if we do real interval field with 53 bits of precision, and I'll make a number, namely pi. So I'll make that A, and I'll make B be real field with, actually I'll make B be a floating point. So this is kind of a worse, wow, crap. My cursor moved. Floating point number pi. And I want to do is time it A times A and time it B times B. Let's see what happens. And you can see that the real interval field multiplication is 320 nanoseconds per loop, whereas the floating point is 103 nanoseconds per loop. In other words, interval arithmetic is really, really fast in Sage. And that is okay. So the next thing is assumptions. So sometimes when you compute a symbolic integral, you'll just get this traceback. And usually when you see a big red traceback, you probably just ignore it and panic. But if you don't, then maybe you'll read to the bottom. And by the way, somewhere on my to-do list is to make it so that you don't see anything except the last line until you click a button, but I haven't got to that. If you go to the very bottom, it says, value error, computation failed since Maxima requested additional constraints. Use the assume command before evaluation may help. And then it gives you some help about how to use the assume command. The situation here is that I'm asking to compute the antiderivative of x to the n, which is just like a really, really easy thing using polynomials in most cases. It's x to the n plus 1 over n plus 1. Except when n equals by 1, I guess I meant minus 1. Okay, except when n, that should be minus 1. Except when n is minus 1. And then, you'd be dividing by 0 and it's wrong. So I don't know if I should fix this right here. I just made a typo. Everybody knows this sort of thing though, because you guys know calculus. Okay, except when n equals minus 1. All right, so what happens is you can tell Sage, and really its integration engine, to assume that n is either equal or not equal to minus 1. And then it will compute the integral accordingly. So that's what we're going to do here. First, forget any assumptions I might have left laying around. And then let's assume that n is equal to minus 1. And then do the integral, and it gives back log of x. Or we could forget that n is minus 1, and now assume that n is not minus 1. And get the integral, and we get this. Okay? So this is one possible issue that could come up if you were trying to do symbolic integrals with Sage. In some computer algebra systems, in the competitor's computer algebra system, it might give back some sort of complicated thing that is like some cases where it'll say it's this integral if n is equal to minus 1, and it's that integral if it's not minus 1. But with Sage, it just gives an error, and then you have to say which of those choices you want to take. Okay, so that's it. I mean, it's just something that may come up. The last thing I want to say a little bit about is SymPy. So SymPy is a Python library for symbolic calculus. The main, or one interesting thing about SymPy for you is that you can use it completely separately from Sage. It's mostly written in pure Python, and it has some fallbacks for efficiency to compiled Python or other code. But it does have a sort of, it's fully usable as pure Python. That means you can maybe run it in a web browser, you can run it from a Java program, etc. There's a wide range of ways in which you can use SymPy. You can use it easily on Windows, for example, directly natively. So that can be really valuable. Or whatever. Okay. So the way SymPy usually comes up in the context of Sage is somebody's been using SymPy and they say, hey, I'm using Sage now because the symbolics are faster. And they're sort of frustrated with certain things about SymPy's symbolic manipulation maybe being too slow. And or maybe SymPy is missing some functionality, like interval arithmetic, or Sage can generally do more complicated integrals, and it's better at computing limits and series and stuff. Because Sage, under the hood, can call out to Maxima, and Maxima is just very well developed, having been around for decades. Whereas SymPy is, it was some undergrad in the Czech Republic started it about when I started Sage, named Andrej Srtek, and he worked on it every once in a while. And then they got a lot of funding from Google Summer of Code, which is probably one of the biggest funders of students working on open source software. Google spends tens of millions every year to fund students working on open source software. And they've many times got maybe 5 people funded to work full-time during the summer. The other way in which SymPy sometimes comes up on the Sage mailing lists is that somebody will say they're trying to compute some integral or series expansion or limit or something in Sage, and it's wrong, and there's a bug. And half the time when people say that, they're just confused, and there's no bug at all. But the other half of the time, they're actually right, and there is a bug. And in many of the functions in Sage, like integration, you can explicitly say algorithm equals SymPy. It's not the default, but in many cases, what it will do is it'll take the expression that you're integrating, move it over to SymPy, compute the integral there, and then move it back. And so it's just like one little flag, you can get it to do the whole integral over there, and you can compare the answer. And so our answer often to such questions is, one, we've reported the bug to the Maxima developers, and two, if you use algorithm equals SymPy, you can see how to compute the same thing, and in fact, the answer is often right in SymPy. If SymPy can do something, it tends to be right. So here's an example of using SymPy. You say from SymPy import some things, and then it's pretty similar, except instead of var, you have symbols, and for some reason it's uppercase limit. And instead of simplify or something, you have a doit function. I don't know, it looks a little silly to me, especially with no underscore, and I don't know, it seems a little too informal, but whatever. It's very powerful. Unfortunately, it doesn't LaTeX things, evidently. It'd be nice if somebody were to add that. So you can see there's no support for like LaTeXing yet, at least. And then, okay, here's an example that illustrates what I was talking about. This is an integral. It's the first one I showed you on Monday. Sine of x times cosine of x times tan of x, just some random product of trig functions. And integral with respect to x, Sage via Maxima gives the first answer. And then all you have to do to see what SymPy gives as the integral is say algorithm equals SymPy. And then it, under the hood, just uses SymPy to do the calculation. And this is actually pretty tricky to implement because for every single special function or expression in Sage, we try to figure out how to convert it to SymPy. And then for everything in SymPy, we have to figure out how to convert it back. And we have to do that in a way that doesn't, subtly change things. So in case that's not possible, it'll just get an error. But if it is possible, you get an answer. Notice here the answer is different. You guys, of course, are so good at math, you'll instantly see they're really the same via some trig identity, but they look different. And you can check that they're the same by doing, simplify full or bool of one equals the other, and that says true. So you get two different looking answers, but they're really exactly the same function. You're only guaranteed that they differ by a constant, but here they actually are the same. Okay, any questions in general about symbolic calculus? All right, so there's 7 plus 27 minutes remaining. So I'm going to stop talking about this. And actually, could we try to, just for like 2 minutes, try to crash this worksheet? I'm curious what will happen if every single person tries to compute something at the bottom of it. Because I'm trying to debug something. And I found certain documents that when opened would cause a lot of trouble. And I'm curious if we can force this to be such a thing. Just try to do something. I don't care what. By the way, if you use Chrome, there's a cool thing you might want to use right now, which is Window Task Manager. What it'll do is it'll pop up and show you the CPU usage of every single tab that you have opened in Chrome. So you can see that, sadly, the CPU usage of this particular one is very high suddenly, which makes me unhappy. Cool, so you have like 25 people all doing stuff to this worksheet at once. Still somewhat responsive. Hasn't completely gone to hell yet. Has anybody's browser completely froze? By the way, the cool thing about, if you're using Chrome again, about this this task manager is that, so if you try to refresh this tab, because the tab is sort of using all the CPU, it can be very hard to refresh. And if you try to do other things in the OS, it's annoying. However, in the task manager, you can click end process, and that one tab will get killed for sure instantly, and then everything sort of restored. So notice if I just click End Process, now there's almost no CPU being used. And then you can, refresh and you're back. Cool. The second thing I was curious about is whether, if I don't have the file open, would there be a lot of CPU usage? Are you guys all doing stuff, or anybody doing things still in that worksheet? No? Okay. Well, just almost no CPU usage. Yay. So again, remember, at least if you're using Chrome, it's really easy to deal with this by Task Manager, kill the task. It's something I didn't know about until a few weeks ago myself. I would always try to kill stuff in the general process manager. Yeah, you have a question?
Like the taskbar for like your computer as a whole, on the top that you go when you go to Window.
Yeah. No, yeah, on an
I have a PC, so.
on a Mac, yeah. This is not for the computer as a whole. This is specific to Chrome. So on a PC, you might find a menu over here.
I have that menu.
Or wherever it is. It's in your normal menu. This is part of the Chrome menu bar. It's nothing to do with OS X. It's purely a Chrome thing. You'll have exactly this task manager on Chrome OS or Windows or anything else. And it only shows you information about specific